Okay.
I know literally zero things about sports, so I'm using the internet to dictate my team. It's an 8-man league.
Well, so, I guess I know a medium amount about football. I don't know. I know quite a bit about, I guess, individual Packers, but not outside of that. So my whole team is just Packers.
Okay.
Like last year, Jordy Nelson started for my team, and he didn't play football last year.
That seems like
He was injured.
Yeah, why would you do that?
Act of solidarity. I mean, that's the point of fantasy football. Is you can. I also this year's draft, I tried to draft Batman.
Yeah, no, was not available.
They wouldn't allow it. I tried to draft a second copy of Aaron Rodgers as a kicker. You're supposed to have fun with it.
Why did we get Vic?
What, Michael Vick? I used to have him. I did used to have him, but now I'm all Packers. And then every year I name my team has like a theme. So I name my team something funny, and then I have like a theme on how I play, and that's not really classroom appropriate, but
You're not recording yet.
I am. Even if I wasn't, it's beyond that. Okay, so tell me about risk processors. What does it mean for a processor to be a reduced instruction set? What's the point? Go ahead. Oh, okay.
Reduced for a simplified.
Tell me more.
To increase performance.
Okay, and how might it increase performance? Because it's simpler.
It's simpler.
I mean, they've reduced it. It's okay. So most of what you said there it has some accuracy associated with it, but you really, I feel, I haven't said anything.
Yeah.
So do you have more to share? Who? Okay. Why? I feel like you're just making crap up at this point. What's an instruction set? Let's start there. When I say instruction set, what does that mean to us? Okay, like in Lippmann terms, I like that. So it's the collection of magic tricks, right? So our instruction set is our collection of magic tricks that a CPU knows how to do. All right, so we have two options in our world right now. We have the generalistic reduced instruction set, i.e. less magic tricks. Then we have the proverbial Intel architecture, the the IA architecture, which is not a reduced instruction set. Doesn't necessarily imply an expanded instruction set in the big scheme of things, but it doesn't claim to be reduced. All right, so we have two different options. We can try to accomplish things with less magic tricks, or we can try to accomplish the same thing with more magic tricks. What's the advantage of less magic tricks? Go ahead.
Less power consumption.
Okay, less power consumption. We have the less magic tricks we have, the less kind of management we have to do associated with those magic tricks. So we don't have to power them. Outside of that, we don't have to find space for them. Okay, what else? Less heat. Okay, so a lot of the things, the last time we kind of had a phrase, we said heat is the enemy, right? So as we come to, inside of our computers, heat is bad. So we want to try to get as much power as we possibly can get from our computers without having too much heat that takes us over the threshold where things start melting and stuff like that. All right, so the concept would be that in a reduced instruction set, i.e. less magic tricks, we'd have less things to get hot, therefore less total heat. Okay? Now you mentioned, I think you were making stuff up, but you were mentioning that it's faster, or they try to be faster. In what way could it try to be faster?
It decreases the runtime per cycle by using having to run less instructions per cycle.
Less instructions per cycle. Okay. I think you're getting on to something reasonable there. So each of these magic tricks, even though from our perspective, a magic trick is this integrated circuit thing. So we apply electricity here, it goes through a bunch of stuff, and then spits out answers on the other side. They are not all equal size, right? Okay, so a reduced instruction set would probably indicate that a single instruction might do a little bit more than in an expanded instruction set. You kind of, if we assume that there is this minimal amount of, here's the list of things that a CPU must be able to do, and we can accomplish that with 50 little tiny granular magic tricks, or we can accomplish it with 30 not so granular magic tricks. That would indicate, well, it would be reasonable to assume that those 30 magic tricks on average might be a little beefier, right? They might try to accomplish a little bit more. So rather than having to call two separate instructions to accomplish the same thing, we might be able to call a single magic trick and have the equivalent of two magic tricks over here happen. Okay, why is that faster? Why is it quicker to call one magic trick? Let's say they both do the same thing. Ultimately, they both accomplish the same logic. Why might it be faster to have a single magic trick that accomplishes the logic versus having two separate magic tricks that combined accomplish the same logic? Okay, so whatever the equivalent hardware version of context switching is for integrated circuit stuff, right? Because we don't necessarily, he's referring to something from the operating systems class where the CPU has to move between processes. Well, the idea is that both of these instructions, both of these magic tricks are on the same process, so we aren't necessarily leaving the CPU, but whatever the equivalent is, whatever the overhead work that has to happen between a magic trick 1 and magic trick 2, okay? What it takes to accomplish that. Now, from our reading in the book, I think we're through first half of chapter 1? Okay. 1.6? Is that right? Is that basically half? Ish, a third, first third. Okay, so from your reading in that so far, I think you've gotten to this point. If you haven't, then this question will be kind of funny to ask. But what are some of those overhead things that happen when when a single magic trick gets executed? What has to occur? Let's see what we got here. So we're going to be talking about 1.5 today. I would think it'd be in here. Yeah, I would think it'd be.
That's terrible.
Oh, are you just laughing at that, or is that where you think it would be? Because we should have like a fetch decode. Does that sound familiar to you?
Well, it's input, output, data path, control memory.
Well, those are the components. But when we talk about a magic trick, we have to first fetch the instruction, fetch the next instruction. Bring that instruction into the CPU. Yep, so that takes time. So fetching an instruction takes time. Not tons of time from a human perspective, but time. Okay, then we have to decode it. What does decoding it mean? What does decoding an instruction mean? Okay, so we're dealing with a low-level language, an assembly-level language. So that means it's going to still look English-like, even though it's a one-to-one relationship with the CPU. Every line of code we write in assembly language is equivalent to exactly one magic trick on the CPU. We still have to decode that because there's still going to be a mapping. Okay, and we're going to see this even more when we get into the assembly language stuff, which we'll actually talk about a little bit today. In fact, I'll actually talk about it relatively quickly here in a few minutes. So the idea is that when we have a single magic trick, a single instruction, we have to map that to the equivalent instruction, the equivalent magic trick on the CPU. And the CPU isn't going to use nice English-looking things. It's going to have, magic trick 0001, magic trick 00010, so on and so forth. That's how it's going to count its magic tricks. So it's going to index that collection of magic tricks, that instruction set, that the CPU knows how to work with, it's going to index those in a very binary, computery way, not in a way that human beings like. We like looking at a single instruction and say, well, that's a little bit more granular than I'm used to programming in, but at least I have a pretty good idea what this guy does. It says move AX comma BX. Well, what does that mean? Well, it moves whatever's in BX into AX. Fine, I'm moving memory around. I have a decent idea of what that kind of sort of might mean. Okay, I might not know how it applies to the rest of these 4 million magic tricks I have going on up here, but I at least can read it and have a clue. As opposed to seeing at the machine level where I'm applying circuit 00010 to memory location 0xabc, comma, memory location something else. That's going to be very difficult for a human being to follow because we don't have all those wires hooked up behind the scenes, and we don't necessarily recognize this memory address as being the address of a certain register. Make sense? Similarly, if we think about this in terms of real life, every one of us in here knows our home address, right? Wherever you call home between when you're not living on campus or something like that, we know our home address. How many of you know your GPS location? I suspect maybe a couple of you might, but generally, thanks to Pokemon Go, I know exactly where I am on Earth. I also know exactly where my Pokemon guy is, and he's not near me. All right, so GPS location is a little bit more cryptic, right? We kind of have an idea of what it means. It gives us a little, a cross-section of where we are in the world. Actually, with elevation, it gives us an XYZ as well. But, we can get an idea. But most of us don't remember our GPS location, even though we could use that to uniquely identify our house in the world, correct? We remember it by an English-sounding address. Easier for us to work with than remembering two, relatively, two numbers that were the significant digits actually are fairly significant. I've always found that fairly interesting with GPS, where you have to go out to probably 4 or 5 decimal places before a tiny change doesn't take you out of your yard. So it's pretty important. Like 43.1 is very different than 43.2 in the GPS world. I mean, you're talking not probably by your house, probably across town or something like that. All right, so in any case, there's a mapping. That's what the decode does. So if we kind of put this, I'm going to put this actually right after risk here. Magic trick process. So we said fetch is number 1. So fetch is get an instruction, or get the next instruction. Decode is turn assembly language instruction into machine language. What happens next? Fetch, decode, then what? Execute. What does execute mean? It means do it. Apply electricity, apply your inputs, whatever the current inputs are, which in hardware talker is usually, in fact, actually, let's pause this here for a second. And most of you have probably seen this before, but I like looking at, especially since we're going to be doing it in Linux in here. Let's do Hello World Linux Assembly. Yep, this will be good enough. All right, so here's some assembly language stuff. Now, I had you also do the assembly language, start the assembly language tutorial. Is that correct? Or have I not done that yet in here?
We read like the first introduction.
That was your reading assignment. Okay, gotcha. I need to probably, here, in fact, so I don't forget. I'm going to put this right, we're going to add a slide right to the beginning. call this progress. So book is through 1.6, and assembly is red intro section. All right, good enough. That's going to help me as I'm bouncing back and forth between this and the grad class. Oh, so let me go back here. All right, so at this point, most of us really haven't seen much assembly, correct? You kind of read the intro. You maybe have a little bit of an idea kind of when somebody says hardware register, what that means, possibly something like that. That's okay. So this is going to give us a decent idea, almost giving us the cadence of assembly language. So when we're talking about writing stuff in assembly language, what we're really talking about is dealing with the CPU on a magic trick by magic trick basis. So dropping down to the computer's level and really understanding how instructions are carried out and how we put multiple instructions together, what ultimately happens. But now we need to start thinking about things in terms of how it has to work at the hardware level. All right, so for lack of a better phrase, I like to think of assembly language as kind of requiring a staging process, where you have to kind of hide values in certain places, very specific places, so that when you actually tell the CPU to go, to execute that command, it knows where to look, okay? And it's going to go and grab the values it needs to do it so that it can actually perform the magic trick. That makes sense? It makes it a little bit cryptic, at least initially, until we start seeing the pattern, where we're always using the same things. The same 4 registers to accomplish this stuff, and each register has a high and a low, and I'll start introducing some of those things as we get into it. But for right now, let's just assume, so at the very high level, when you read the introduction to assembly, did it talk about AX, BX, CX, CX? All right, that's fine. So let me just introduce that at a very high level here. Okay. So let's go right after this. All right, so we have these things called registers. Let's call them hardware registers. Really fast memory that lives on the CPU. That's what a hardware register is. I often refer to it as a variable made of hardware. So kind of RoboCop, but instead of a cop, it's a variable. And less guns. But still has the cannon, I think. Now, you guys have seen RoboCop, right? Oh, they did a remake a couple years ago, didn't they? It's not like the original. I think they did a remake a couple years ago. They remade everything. All right, so hardware register, really fast memory. Sits right on the CPU. That's our kind of our point of entry when we are writing assembly code, when we're using these magic tricks. They're having to manipulate values stored in these registers. Okay? Now, we've already kind of discussed that we have limited real estate available in our CPU. So in this course, we're really concerned, at least probably the first half of this course, about the CPU itself. And there's a lot of stuff that we need to fit on that little chip that we rely on to make our modern computer work, right? So we've already talked about this kind of, I don't know, magical list of magic tricks, whether it's reduced instruction set or not, whatever that is. There's many. Correct? And each one of those takes up space, and each one of those gives off heat. So part of our real estate has to be for dealing with heat dissipation and stuff like that. That's going to also deal with the material that it's made of. So we'll talk about that here in a few minutes as well. All right. So, but also on that processor, we need to house memory, places to store stuff to be used by multiple magic tricks. All right, we need temporary places, otherwise we can't remember state. Can't remember the current process state. All right, and this is at the hardware level. So if I'm in the middle of performing a series of 5 magic tricks, I need to be able to take a picture of the CPU right now and kind of know what is the current state of things at the CPU level, or even beyond that. But for right now, let's just think about the CPU level. So what does the world currently look like that this next magic trick is potentially impacting? That makes sense? So we have these things called hardware registers, and there's several hardware registers, but I'm going to just talk about 4 of them right now. Those are kind of our go-to starting moves. So we have AX, BX, CX, DX. Now, each of these has kind of a go-to use. That doesn't mean that you can't use it for general purpose needs, but some of the go-to uses are automatically used by certain magic tricks. So as an example, CX is typically called the counter register. Okay, these guys are all, so what are they, 8-bit? 8-bit registers. Am I lying to you? No, they're 16-bit registers. These are all 16-bit registers. Doesn't matter to us right this moment, but these are 16-bit registers. So this guy can hold a 16-bit number, but it's automatically used by many magic tricks that rely on counting. So for instance, loops. All right, so this counter is automatically the counter that controls it. So we would manipulate this value to manipulate our loop. Okay? That doesn't, but physically, CX and BX and AX and DX are all the same. They're 16-bit little memory chunks. All right? They can hold 16 zeros and ones. So the fact that CX is commonly used by many magic tricks for counting is more of a, a convention as opposed to a necessity that CX is somehow wired differently or something like that. All right, so we're just going to talk about these 4 at the highest level right now. All right, so we have a rough idea on what a hardware register is at that 25,000 foot view. Hardware, a variable made of memory. I'm seeing a picture. What is it? Is that the helmet?
Work in progress.
All right. It's Mr. Gonzalez's Packers helmet. Did you guys see the Facebook post of Mr. Gonzalez going to the water park this weekend?
No.
Yeah, he got his...
Did he get baptized?
No, but he got his own swimsuit. I called it his bling swimmer smock. And if you're on Facebook, what I just said will make sense to you if you see it. But yeah. By the way, rule of thumb: don't go to a Dells water park on Labor Day weekend when it's $5 tickets.
Like no one there, or
No, everyone.
Everybody was there.
Oh.
There was a 45-minute wait for the hot tub.
Wow.
There was a line for the hot tub.
You just get in there and post out the rest of the day.
No, I didn't want to wait in the line, but that's what I would have done. Yeah, and I ended up having to rent a cabana. There was like no chairs. So I spent like $80 to like rent a private cabana tent thing for we had 5 people. And I just slept in there all day.
Nice.
Yeah, I don't know. Kind of like my Tempur-Pedic mattress a little bit better.
Wow.
Oh yeah, Mr. Gonzalez played some World of Warcraft this weekend too.
That new expansion.
Yep, it was solid.
Demon Hunter.
What's up?
Is he Demon Hunter?
No, we only played that for a couple levels. It sucked. We're playing Druid. All right, so hardware registers. We have 4 different memory locations. Each of them are 16 bits. They're all built the same. They just happen to have some conventions. All right, so we're good there. Let's go back to our assembly language example here. Now, for starters, this is an assembly language program written for Intel processors, but for the Linux operating system. So before we go any farther with that, why would the assembly language for Hello World in Linux be different than the assembly language for Hello World in Windows if they are both using Intel processors? So now we're trying to tie some of those strings together, dealing with the difference between the processor architecture and how software marries to the operating system as well. So what does the architecture mean? When we say that this is a Intel architecture, an IA processor, as opposed to a PowerPC RISC processor, that's going to dictate things like the AX, the BX, the CX, those guys, as well as the collection. There's about, I don't know, let's say 20 combinations of registers and flags that mean different things, like zero flag and carry flag and that kind of stuff. So those things are like, here are your hardware tools that come with a processor of this architecture. Okay? Fair enough? Now, how many of you are Mac users in here? All right. What kind of processor is in your Mac? Some kind of Intel processor, unless you're dealing with a very old Mac, right? Okay. How many of you are Windows users in here? Okay, a bunch of you. What kind of processor is in your computer? Intel. Intel processor. Intel compatible processor. All right. How many of you are Linux users in here, or who ever run Linux? We have 2.25 people who have run Linux. Okay, whatever. Okay, so what you did is you dual booted your Windows machine or your Mac, and okay, so you had a Raspberry Pi. That actually kind of breaks this discussion, so pretend that doesn't exist. Because Raspberry Pis run a RISC processor. They have an ARM chip in them, yeah.
Isn't the newest one have a different thing in it?
Possibly, yeah, because I think they can run Windows, the newest one, yeah. But in any case, so for most of us, if we've dabbled with Linux, what did we do? We dual booted our computer, we create a partition, install Linux on it, so you reboot out of Windows and exact same computer hardware, but running a different operating system, right? So now you're running Linux. So on all three of those operating systems, we're running the same architecture, the same hardware architecture, some flavor of Intel. All right, so if it's the latest, greatest one that just came out last week, the processor might have, it possibly has another register. I'm actually not sure what the current latest, greatest thing is. I don't think they're really adding registers anymore. Mostly they're doing things called pipelining, which are making certain things faster and then adding magic tricks to the CPU to make common tasks quicker as they get better and better at making things smaller on those chips. All right, so punchline is if we're writing assembly language for an Intel processor of any sort of somewhat recent vintage, we're dealing with these AX, BX, CX processors, and there's EAX, EBX, that kind of stuff. All right, that's the architecture. Now, the operating system itself, though, this is where our assembly language, we write an assembly language program for Intel architecture for Linux, where it might look different than a program that accomplishes the same thing, in this case, Hello World, on Intel architecture, same Intel architecture, but for Linux or for Windows. I don't remember which one I said first. All right, so two separate operating systems running the same architecture. And the reason for that is, how many of you in here have had the operating systems class or are currently in the operating systems class? Okay, so one of the things you're going to be talking about in there at some point, or have talked about in there, is this idea of system calls. Okay, so every operating system, think of an operating system at some level as being like a software-based CPU, right? There is a collection of magic tricks that an operating system knows how to do to carry out common tasks, like put stuff on the screen, display, in this case, Hello World to the screen. That makes sense? So we would call that one of our must-have features of all operating systems. They must be able to put things on the screen so we can see it. All right, so we'll leave it at that for now. Every operating system is going to have its collection of system calls that allow it to do that kind of stuff. Now, some might have a larger collection than others, but it's kind of that operating system's approach to how do we act as that middleman between the human being, us, in case you weren't aware, especially a couple of you over in this area. You're people. Yep, I know. Okay, so us, the operating system acts as the middleman with the hardware, which is what we're talking about in here. All right, so we have this thing that you're talking about in the operating systems class, which sits between us. And that guy provides some software-based magic tricks that allows you to say, I want this to happen, and it translates that to something to the actual CPU. All right, so I think we can all agree that no matter what operating system we're working with, they will all at the very least have the capability of displaying something on the screen. Kind of a must-have feature of all operating systems. All right, fair enough. So here's an example of us getting Hello World on the screen in Linux using Intel architecture assembly language. So we're speaking the assembly language commands, the instructions, that all Intel processors understand. Specifically, we're leveraging the system calls that Linux is providing to us. Okay? And you're going to see what that means here in a second. So I'm not going to go into too much of this stuff up here, but we have our text section. This is the where the source code is, which this is the human-ish readable assembly language source code. All right, and then we have, this is our kind of our main. Program starts here, global start. All right, so this guy right here is called a label. So labels are always the text followed by a colon. And then we start having our list of instructions. Okay? Now, before we start looking at these list of instructions, I want to go down to this other section here. So we have two sections represented in this little program. We have our text section up here, which is our list of commands. And then we have our data section. So data section is the place for us to put like our variables. All right, that's where we define things that we're going to remember. And one thing we want to keep in mind here, just at least at the high level, is there is a difference between a variable and what is currently stored in a register. Okay? So variables are linked to things stored in system memory. So like your 16 gigs of RAM or your 8 gigs of RAM, whatever it is. So system RAM is fast compared to a hard drive, but slow compared to registers. So whatever you put in registers is turbo speed. That's as fast as you're going to get, is what you put in our register. All right, so what we're going to see here is pretty much at the end of the day, everything before we execute gets thrown into a register because that's going to be the place where it can operate at the quickest speed. All right, but that doesn't mean that we can't then also temporarily leverage system memory for holding on to things in between instructions, because we do have a limited amount of hardware registers. We can't just store all the variables we ever want inside of a hardware register, A, because we have a limited number of them, and B, as I've already kind of alluded to, those hardware registers are required places. Like we talked about CX as being kind of the go-to counter for many magic tricks. We really can't just randomly put stuff in CX because some system call we might call might need it and might change it and that kind of stuff. All right, so we're going to want to keep our data we need to preserve in the extraneous system memory and then bring it into registers the moment we need to actually use it. Kind of make sense? So in our data section here, this is where we are actually defining our variables, linking values, constants if you will, literals, to named places in system RAM, not in a hardware register. So we're creating a variable called message, MSG. This guy is going to be a data byte. We'll talk more about those types. So think of that like our primitive types in Java. So one of our primitive types is a data byte. And we're putting the string hello world in here. All right, and then this guy right here is an offset off of a base address. Don't worry about that right now. Just we're storing the string hello world. All right. Then in another variable called len, which is going to represent the length of that guy. Okay, we could have named these variables whatever we wanted. They're just variable names. Okay, we're letting this guy equal the length of message. That's how we get the length of a string message. Okay? And what it actually does is it takes the base address and it counts the number of bytes across there. So we'll talk about that, but that's what those two are. Go ahead.
Looking at the top of section text, does anything in there, like you see the variable in section data message, and then you also see message in section text, do those two conflict at all?
They don't conflict. This is where we're defining our variables. This is where we're using them.
Oh, okay.
Yep, we're about to go and talk about that right now. Yep. So the text is here's the instructions I want you to need. this is the instructions we want the CPU to carry out. And then our data section here, which can come before. We can put our data section up top if we want. These are the variables that we're going to need while we're working with that. Okay? All right, so we have two variables, one holding the string, one holding the length of the string. Now we'll go to our actual code. Now, remember, I kind of said that one thing that you want to think about how CPUs actually work is you're almost staging things. You're setting up things in certain hardware registers before you pull the trigger and tell the operating system to perform one of its system call magic tricks, which is reliant on data being in certain registers. All right, that's the cadence that assembly language uses. So the very first thing we're doing is we're taking this register EDX, which is a 32-bit register in Intel. So this is, for the all intents and purposes right now, just pretend like this is AX, BX, CX, and DX. We're dealing with a 32-bit register here instead of a 16-bit, a 32-bit processor rather than a 16-bit processor to keep it simple, but whatever. So the very first thing we're doing is we are moving the value. So this is the destination, and this is the value we're moving into that destination. So we're moving the value of length, which is going to be the number of characters inside of our string, hello world. We're moving that into this hardware register EDX. Hardware register is really, really, really fast. So EDX is going to hold the length of our string in really, really fast memory. Then we're moving the value of message into ECX. All right, so now we've moved the values of those two variables into really fast memory. Then I'm just randomly moving the number 1 into EBX. Okay? Now, where does the number 1 come from? This is where we're seeing our hardware linked to our operating system. So inside of Linux, it has a thing called a file descriptor, an FD, and those of you who took systems programming last semester, we saw those with everything was a file in Linux, right? So we have a thing in our file descriptor, and there are 3 built-in file descriptors in Linux. System out, system error, system in. Okay? That's standard out, standard error, standard input. So standard output, which comes built in, it comes with Linux, happens to be file descriptor indexed 1. File descriptor index 0 is standard in. File descriptor index 2 is standard error. All right, so this line right here requires that we had the knowledge that the file descriptor for Linux, standard out, this is ultimately going to be where do I want to write hello world. I want to write it to standard output, which is the monitor. We have to know that value of that, because we can't just put the word standard out there. We could have created a variable down here called standard out and put a 1 in there, right? And then move the value of that variable in there so it maybe looked less cryptic. Instead of us just looking at it and saying, well, I'm just randomly moving a 1 in there. Okay, whatever that means. This relies on us having some knowledge about the system calls of the operating system. Make sense? All right, so I'm moving 1 into EBX, and then I'm moving, again, randomly, 4 into EAX. And 4 corresponds to the Linux system call syswrite. All right, so if you think about the magic tricks that Linux is going to provide, number 4 on that list is a magic trick called syswrite, and it probably has a little paragraph next to it. It says, this writes the value that is stored in ECX up to the number of bytes stored in EDX to file descriptor stored in EBX to the screen, or to that file descriptor. That's what it does. So that's what the syswrite system call does. It looks in EDX for the length, ECX for the actual thing it's writing, EBX for where it's writing it to, and then it fires. So we can think of this guy as a function that requires 3 inputs. All right, but in Java, if we were calling a function that took 3 inputs, we would pass it 3 parameters, right? 3 inputs. We don't have that luxury here in assembly language. we had to stage our 3 inputs into some hardware registers for this guy to operate on. Make sense? So that's what we did. We staged everything. These are the 3 inputs that that system call needed. Then we stored our system call inside of EAX, so we really staged 4 things. And then this next line is kind of the critical thing. This is the execute line for this. We interrupt the CPU. So something Dover mentioned earlier was this thing called context switching, right? So tell me a little bit about context switching for the as a preview for those of you who are in 350.
Basically, when one process is done doing the things that it needs to do, or it's time when the CPU is run up, it's time for the new process to come in. So they have to do context switching, which is the process of them switching from one process to a new process.
Okay. So context switching is the enemy of performance on our in an operating system. So the job of your operating system is going to be to fake us out as end users to make us feel like we're getting all the attention of the computer, whatever that means. Okay. Well, we also have multiple programs running on the computer at one time. And those multiple programs all have to be faking us out, thinking they're all running with the full power of our CPU and all this stuff. Okay, so that means that each one of our programs is getting a little bit of CPU time in terms of actual, milliseconds. Human beings don't really read time that way, but they're each getting, we're going to work on Microsoft Word, then we're going to work on Instant Messenger, then we're going to work on your email, in a big fast loop, so that from our perspective, it's all getting plenty of love. Okay? The context switching occurs when the CPU stops working on your email, puts that on hold, and moves on to the next program it's going to work on. And that context switching takes time. It's not necessarily measurable time from a human being's perspective on a one-off. That is, the time it takes to context switch once, we wouldn't notice. But if we context switch thousands of times in a short period of time, we will start noticing. Things start getting sluggish. All right? So even though computers are operating at a speed beyond what we we recognize in real life, if there's enough delay, we certainly notice sluggishness, right? All right, so that's an operating system concept, the context switching. But that concept is reflected, it is duplicated at all sorts of different levels. Whenever you change from doing one thing to doing something else, there is a transition period. Real life, if you change from cooking dinner to cleaning up the kitchen, there is a transition period where you go from cooking mode to cleaning mode, right? You start getting out the cleaning utensils, you get the plates off the tables, you can start wiping stuff down. There's a transition period, right? Same thing true here. That's what context switching is. All right, context switching, the thing that says, okay, it's time for you to stop, you're done processing this program, the way for it to happen naturally is to interrupt the CPU. Now, those of you who've had 350, what other things interrupt the CPU? So when does context switching happen? It happens when we have naturally run the course and it's no longer our time for the CPU. Our time is up, right? We've gotten our 10 milliseconds on the CPU. Now it's somebody else's turn. So we're interrupted and so we have to context switch out to give the CPU over to somebody else. What other circumstance happens that causes us to context switch? No. Who in here has already had 350, not currently in it? Okay, 4 people. All right, so why aren't all 4 of you answering this correctly right now? You played a video game? Are you lying? Yes, I'm lying. As I see him do like this weird like shift, control shift Q C, it just switches it over to note mode. So we have 2 ways that the CPU gets interrupted for a context switch. One way is its time is naturally up. The other way is I/O. It's input-output time, right? So the CPU has done as much work as it possibly can do, but now we need input from something else, right? We need to write something to the screen. We need to read something in from the user. Whatever it is, it's something that is slow, and therefore we're not going to pause the CPU. We're instead going to interrupt the CPU, get the current task off of the CPU so it can go and do its quote, slow I.O. thing, and let the CPU work on something else. Make sense? All of you who've had 350 remember this now? The I.O. is slow, so we're not going to stall our CPU with I.O. stuff. So we interrupt the CPU right here. Here's our magic trick, which interrupts the CPU. That's this guy right here. So we're interrupting the CPU. Specifically, we want the CPU to call the kernel. Now, what's the kernel? Is that the KFC guy? Extra crispy. They have a spicy one now? I've seen the guys like super tan or something like that. You know, it's got some name. I wanted to try it. All fat people do. Pretty sure. All right, so what's kernel mean there?
OS that is the actual OS and contains all of the really important things that we should have access to.
Yep, so this is the actual operating system. So when we say things like Windows 7 or Linux or Mac OS, when we say Windows 7, the distribution is called Windows 7. The actual operating system is the NT kernel, which is under the hood. That's the core operating system of that guy. And then all those other programs that come with Windows, Notepad and all that stuff, those are all part of the Windows distribution to make it, you know, a full-fledged operating system for us. Linux, it's the Linux kernel. Very imaginative. All right, naming. So right here, this is how we reference the kernel. We're talking to the actual operating system. We're interrupting the CPU and say, call the kernel. All right, and what does the kernel do? So based on what we've done right here, what do you suspect the very first thing the kernel does is? Turn this into another quiz. It'd be a good quiz. If you're the kernel, okay, and I've just interrupted the CPU, I said, kernel, ball's in your court. Kernel's turn to do their thing. What's the very first thing you suspect the kernel does here, based on what you see on the screen right now? You're the operating system. Time to start connecting some dots. Do you suspect that the kernel has a very close working relationship with the CPU? So kernel probably has the ability to look right at registers, some level. So these registers that we really can't go in and manipulate as a high-level programmer, chances are the kernel, the actual core operating system that sits between us and the CPU, it has access to those things. So what's the very first thing? If you're the kernel and the CPU's just been interrupted and it just stares at you, okay, your turn. What's the first thing you do based on what you see here? Store the data that's in the registers? All right, so I'm gonna advertise this as what we spent the last 15 minutes talking about going through these commands wasn't for our health. These commands mean something. The answer is somewhere in those 4 lines. What is the very first thing you suspect that the kernel will do? Remind me, what did we do with this line? What are we accomplishing with that line? Yeah, we're storing the length of the message in a register. Fine. What are we accomplishing with this line? Storing the actual message in another register. Good. What are we accomplishing with this line? Okay, so we're storing the number 1 in that register. Just happens to, because I don't want to get ahead of ourselves here. All we're doing there is storing the number 1 in this register. You happen to be kind of getting ahead of us, we already talked about it, but saying that that 1 actually means something a little bit more than just 1. It's got a real purpose. Okay? What are we doing right here?
It's not telling it to do it. It's putting a 4 there, which means that the system should do a syswrite.
Okay. All right. So we want to take what we just heard in the last 15 seconds. All right? We're storing a 4 there, which is an arbitrary 4, fine. But that 4 happens to mean something under the hood. You said that it means that we're going to be doing a syswrite. And that syswrite implies something. What does syswrite imply? Yeah, that we need 3 things. All right, so let's go back to our question now. And you're not allowed to answer. When we interrupt the CPU and talk to the kernel, what is the first thing the kernel does? Go ahead.
It checks the EAX.
Yep.
See what function is getting called, and then it goes through the next, well, depending on how many parameters it needs,
Yep.
it goes through those.
Very first thing he does is he looks in EAX. EAX has within it what the kernel is supposed to do next. So if I'm the kernel, I'm going to peek in EAX, I'm going to find a 4. The kernel's going to say, okay, well, what does 4 mean? Syswrite. Opens up his manual. What does syswrite say I need? It says I need a length, I need a message, and I need where you want me to write the message. I got the rest of it. Okay, because I'm this really complex operating system that somebody really smart wrote, and I know how to ultimately write stuff to the screen, but I'm going to need those 3 pieces of information from you to do it. Make sense? Okay, so the very first thing the kernel's going to do is going to look in EAX. It's going to find out what it needs, and effectively for us here, because we have a 4 in EAX, the kernel now knows that he needs to look in 3 other places. It's going to look in EDX for the length, it's going to look in ECX for the message, and it's going to look in EBX for the destination, where we're going to write that message. Make sense? And it's going to go and do those things, and then ultimately it's going to write the message. It's going to do the magic that is syswrite. Now, what is syswrite? So we've kind of advertised it here as a function, right? Okay. Well, since it's an operating system, it's probably not a circuit. Okay. But the idea is that it's a program, right? And chances are it was a program written in a high-level language like C. If it's Linux, Linux is a C-based language or a C-based operating system. But at the end of the day, won't that language become assembly language? How does a C-based program become assembly language? It's compiled. So at some point, we took this program called sys_write.c, probably the name of it, and it got compiled down to its object code, and ultimately that got linked together with a bunch of other stuff, we'll talk about that, and became a giant list of instructions that the CPU knows how to do. Okay, now that's kind of beyond us. Okay, somehow it figured out, because what does syswrite ultimately have to do? It has to start dealing with the graphics card at at an individual pixel level, stuff like that. So there's a lot of really complex stuff that's happening inside of that syswrite. Okay, and we're pretty happy as low-level programmers right now that we didn't have to write that ourselves. Okay, so for a second there, we were really depressed that, oh, well, this is a lot of work to do hello world. But the point is, it could have been a lot worse. We could have had to write syswrite ourselves. So that's the importance of that operating system. Okay, the importance of the operating system exists at 2 different levels. On one level, it helps us as human beings interact with our computer because we like to point and click and use the mouse and all that stuff, right? Okay, but it also helps us at the software level as a programmer because that operating system is providing those high-level go-to moves that we need to do often, like writing stuff to the screen. It's providing whatever the nightmare assembly language likely looks like for that we can just call simply by throwing this value in this register. And even though this guy probably has thousands of lines behind it, from our perspective, all we had to do is stage 3 pieces of information. Make sense? So it could be a lot worse. All right, so stage 4 things. Call interrupt. Very first thing it does is it looks in EAX and says, what am I supposed to do? Ah, you want me to do a sys write? Great. I'm writing it to here. What am I writing and how long is it? I'll go and do it. Done. Now we come back. Very first thing we do. So now this program has gotten CPU time again. So when you guys are in your operating systems class, you'll be talking about things like the program counter and things like that for context switching. So eventually, when we interrupted this program, it left the CPU, turned it over to somebody else who could make use of the CPU while this stuff was happening. Okay? Now this guy's come back onto the CPU, and the very next instruction he's supposed to execute is this guy right here, EAX1. All right? Now, we're putting something into EAX. We're putting in a 1. And over here you see that 1 actually is associated with system call sysexit. So 4 is syswrite, 1 is sysexit. So we move something into EAX, we interrupt the CPU and call the kernel. What's the very first thing the kernel does? Checks EAX, or AX, however it is. So it checks that 1 register and says, what am I supposed to do? And what does it say to do? It says, do number 1. Well, so he looks up in the manual and says, well, what is system call number 1? System call number 1 is sysexit. Fine. Now, evidence here says what? How many parameters does sysexit need? None. How do you know? I didn't give anything, right? It's not after this. Notice that up here we did syswrite, and this guy needed 3 staged things. This guy down here was sysexit, and we gave it no staged things beforehand. So one of 2 things is true. Well, one of 3 things is true. We've written bad code. It doesn't take any parameters, which is the correct one. Or possibly we were able to reuse some of the things we did up here. Maybe it took 1 or 2 parameters and we happen to already have the right values in those registers, which could be a little confusing then, right? It's technically quicker to just use the old values, but then at the same time it's like, yeah, who knows if it's the correct data? And also if we're looking at this in chunks, we don't know that was the parameter. So in this case, it takes no parameters, because we would have expected to see some staging happen before we move that into EAX. Now, along those lines, and then I'll come to you. So along those lines, could I have moved 4 into EAX before I moved length into EDX? Could I have done it right here? Would that have broken anything? So could I have done these 4 lines in any order? Are any of those reliant on each other? Yeah, none of those are reliant on each other. Now, if you had done move length into EDX and then move EDX into ECX, then they start becoming reliant on each other, right? You know, if you're changing a register, then using that register 2 lines later, now those things, the order is important. In this case, each one of these lines is mutually exclusive to each other. They happen completely independent of each other, and they don't have anything to do with each other semantically right now. They only have semantic meaning relative to each other when we do this. So the only thing that's important here is these 4 lines must occur before this line. We can't just randomly put this line somewhere in the middle, otherwise worlds collide. All right, and it's bad. All right, go ahead. What were we going to say?
So for the register, does it matter which of the length message or the descriptor goes in which register?
Yes. Yes, it absolutely matters. This system call, the documentation for this guy will say, I will look for length here. I will look for it exactly in EDX. I will look for the message exactly in ECX. So you have to definitely stage it in the right place, just not put it in those 3 registers and hope for the best. This is the memory address it's a memory offset of the kernel, of the actual operating system. So when the Linux kernel loads itself into memory, through with this thing called bootstrapping, when it actually loads itself, it puts itself, its starting point, if you will, its phone number is at 0x80. So this command says interrupt the CPU, specifically hand the reins over to this guy. Does that make sense? That's a little bit of a simplification, but that's most of the way there. Yeah, this is interrupt. Interrupt. All right. Other questions about that? So notice, now that we've kind of walked through it, it's not so bad, right? Definitely different. Okay, it's a different way of going about it. But if we had a list of our system calls and the parameters it took and where we're supposed to put everything, we could kind of pull this together, right? You have to be a little careful at first because it's kind of paint by number, isn't it? In some ways, it's easier than Java. It's more tedious, but in some ways, it's easier because when you're solving a problem in Java, you're kind of thinking about the solution at a higher level. And remember, historically I've always harped at this idea of breaking problems down into their baby steps, right? Okay. We have no choice here but to do things at the baby step level, because every line is a baby step. Make sense? So in some ways, this is actually kind of a good way of learning programming and then a way to appreciate those high-level languages, but we tend to do it backwards because this is intimidating stuff to look at. The second you're starting to work around with circuits and just that granular level of dealing with the CPU directly, it becomes an intimidating type of exercise. Okay, so that's Hello World in assembly language for Linux. How do we suspect this might change if we looked at this at assembly language in Windows? So I'll do the search for it here. But I want somebody to tell me first before I click on something. Okay. So possibly the interrupt, the location of the kernel might be in a different place. Potentially, yep.
Function names, like the MOV, would that be?
Those guys should be. Those guys are part of the Intel architecture. So as long as you're still running on Intel, the same series processor, if they're the same lineage Intel processor, those should be the same. Okay, but certainly position of kernel could be a thing. What else could change? What was syswrite? Well, syswrite is a system call that belongs to who? Belongs to Linux. Now, do we suspect that Windows likely has a equivalent-ish? Windows can write stuff to the screen, right? Okay, it's not a broken operating system, right? Okay, Linux can write, or Windows can write stuff to the screen, but it might not be called syswrite. It might rely on stuff in different registers. It might require more or less parameters. So those are the things that would change. So let's see if we have a decent example here. It's actually it is the same. Yeah, and actually even this is the same. Yeah, this is 80 hex as opposed to the other thing saying 0x80, which is 80 hex. So there's just different ways of writing the same thing. All right, so yeah, so this happened to look the same. But we did have some opportunities for there to be a little difference.
Oh, there's no start.
Oh no, I can't see what I'm doing wrong.
Can't see what I'm doing wrung. What do you
I'm
mean?
saying that this is the problem post.
Oh! But the stuff still looks the same.
Okay.
I mean, most of this is going to be the same, anyways. We don't want to use pushes and stuff. Let me see if I found a different example, but it is mostly the same, anyways. Code cop. No, I don't want to use pushes. That's just another so for those of you, well, we've all had the programming stuff. So what's push? When you see push, what does that mean to you?
This is the first thing off the first something on the stack.
Stack. We're dealing with the stack data structure, right? So pushing something pushes it onto the top of the stack. Popping something removes it from the top of the stack. All right, so every one of the things, and we will talk about in here, every computer has a stack associated with it that we manipulate. So this is manipulating stuff on the stack versus storing things in memory. So we already have some built-in system memory that's stored in the stack. Rather than putting things in individual variables, we can push and pop stuff on the stack. All right, so regardless, we can sit there and keep searching, but we kind of get the idea that even though they're both Intel-based assembly, and they should look very similar in terms of, I mean, just by that push-pop stuff, you can see that there are multiple ways we could have accomplished it, but the go-to way of getting something to display onto the screen, as opposed to, I'm guessing one of those other ones was probably having it display within an application on an iframe or something like that, as opposed to like just out to the terminal, is all going to be pretty much the same using the same computing architecture, but might call a different number system call, which might take a different number or type of parameter, that kind of stuff. Okay. So that's, we talked about that. You guys did your paper this last week on AMD 64 versus Itanium, correct? Okay, and kind of the punchline was just to focus on why AMD 64 was kind of ahead of its time and where Itanium fit in there, and kind of maybe if we were going to summarize that in a couple of sentences, we might say something like, Itanium wasn't really a success, but it wasn't as big of a failure because you had 64-bit architecture married to software that would run on the 64-bit architecture. You just didn't have enough extra consumer software applications that were 64-bit compliant that would run on the 64-bit version of Windows NT for Itanium. The reason AMD kind of flopped with the AMD 64 is they sold that as a consumer chip. Itanium was special purpose to begin with. Consumers were not buying Itanium chips. It was a businesses, enterprises. All right, so when you have Itanium was. Yeah, Itanium was intended for servers. So the people who were buying that chip were, let's say, knowledgeable. Whereas the AMD 64 was for consumers. Normal folk who were buying it for their home PCs, right? They're getting they go to Best Buy and buy a computer that had an AMD 64 in it, and 64 must be better than not 64, so it must be good. But the reality is that even less consumer software was available for 64-bit. So AMD intelligently, so they thought, made the chip backwards compatible where it could run 32-bit code. But that was actually running 32-bit code at a slowdown because it had to drop into 32-bit mode and emulate a 32-bit chip on a 64-bit chip. So it actually made the chip slower. You'd be better off running a native 32-bit processor on a 32-bit program on a native 32-bit processor than a 32-bit program on a 64-bit AMD processor. That make sense? All right, so for next class, we're going to have you do some more stuff from the book. Keep in mind, I can see reports on the book and see who's doing what. So I think we actually did okay in here, but I can definitely see individuals who have opened the book, done the work, filled out the little quizzes and that kind of stuff. So you'll be found out if you're not doing it. Even though I'm not grading it, I won't take any sympathy on you when you bomb something and I say, oh, you haven't done the book. All right, so we've gone through 1.6. All right, so we definitely want to do that. Let's do the rest of chapter 1. So for Thursday, go through 113. Let me look at the exercises here. You don't need to do all those. In fact, let's actually do this. Go 1.7 through 112. Doing all the exercises and stuff like that, and then I'm going to give you a subset of these exercises to do over the weekend. That'll be your next homework assignment. All right? So read and complete the quizzes and stuff through 112. Make sense? All right, I will see everybody on Thursday.
Yeah.